Okay guys, so we're going to look at a couple of examples just to practice what we've learned in the previous video about what a polynomial is, right? They're our new type of function that we're focusing on. Remember, as we saw in the matching, polynomial functions can look like linear functions like you've seen before, right? Or a constant. Remember, that's just like a horizontal line, or y equals 18 is what this looks like. So it can look like that. It can look like slope-intercept form graphs like the green one. It can look like a parabola like our match over here. So there's lots of different ones, right? Lots of different shapes, lots of different ideas. The big idea that we saw was the end behavior for how we can kind of put them all together. So we're going to kind of use those ideas as we do some sketching. And one tip for sketching is that finding the zeros of the functions is really useful in helping you sketch. And so we're going to kind of keep zeros or x-intercepts in mind. And the goal is just to have a sketch of this graph. And we're going to practice some of our vocab here on the side. Right? We're going to practice our new vocab words. So the leading term. Remember in the previous video, I think this was a really good example right here. 5x to the 7th power, that was called the leading term of f of x because it's the highest power for x's exponents, right? 7 is the biggest power. So the leading term is the whole thing. The leading coefficient is the number in front, and the degree is the power. And that degree is what makes it the leading term. So if we look at this one, for instance, number 1, our leading term is the first term, right? Highest powered, typically we write them in order. Sometimes we don't, so you want to be careful to double check. So the leading term is x cubed. You can think of that as 1x cubed if you like. The leading coefficient is then 1, right? It's that 1 that's really in front. And the degree, kind of color coded, is the 3, right? That's the power. So if you want to write it all out, you can think of it like this, right? Like these 3 kind of go together to make 1 x cubed. And I'm kind of color coding it there to show that piece off. The constant term is what's tacked onto the end with no x's, right? It's just a plain number. So that's going to be our 18. Okay. And then we have to decide what the vocab word is. We can use this to go back, right, and remember the vocab words if we need to. For this one, I'm saying the highest power is a 3. 3 makes me think of like 3 tricycle. So cubic is going to be what I call it. Cubic because of the degree being 3. That's kind of a good connection there to notice. And then the end behavior, let's think about it. So we have an odd power, right? And in addition to being an odd power, we have that the coefficient 1 is bigger than 0, right? That yellow 1, coefficient of the leading term. So if I look back, right, odd, so I'm in the purples, purple highlights, and coefficient being bigger than 0, that's going to look like this guy over here. Okay, so I know it's going to go up on the right, do something in the middle, and go down on the left. There's actually a way that we describe this, what is going on here with the end behavior. To describe that end behavior, I'm just going to maybe scooch this note over here, just out of the way from me. The way we describe it is that as x, actually, maybe I'm going to wait off because I want to maybe have the picture to see this. So I'm going to come back and add something to the end behavior once we have our picture. The zeros, in order to find the zeros, we're going to have to factor this. So I've got x cubed minus 2x squared minus 9x plus 18. I'm seeing 4 terms, so we're going to see factoring continue to come up, right? I'm going to group it into 2 groups, and then I'm going to find the GCF in each group. So first pair, they both have x's. There are 2 x's in common. X squared times x would make x cubed. X squared times the 2 will make 2x squared. And then I'm going to pull out a negative 9 as the GCF for this one. Notice then I would get a positive x. And a negative 2 times negative 9 would make a negative 18. I'm going to call this, right, my greatest common factor. It's like the bigger overall GCF. I'm going to pull that out. And left we have x squared minus 9. Notice if you were to redistribute the x minus 2 into the x squared minus 9, you'd be back to where you start. Do notice, we want to double check, are we done? This guy looks familiar. So you can continue to factor that. Notice two terms. I'm seeing an x squared and 9 is a 3 squared. So that's going to be our difference of squares. Plus 3 and minus 3. Remember, if you multiply this out, you get a 3x and a negative 3x. That's why there's no middle term. You can also view this as x squared plus 0x minus 9 and solve it or factor it like a regular trinomial. So here we have factored form. That means by x-intercepts, I'm going to list them over on the box on the side. What plugged in would make 0? So what minus 2 makes 0? It could be 2. So 2 comma 0. What plus 3 makes 0? Negative 3. And what minus 3 makes 0? Positive 3. So I'm just going to partition that out. So I've got 3, negative 3, and 2. Okay, and now I already know the end behavior, right? I know that it goes up to the right. So I know it's got to go up here. And I know it's got to go down here. Right? I also know something else. If I was to think about my y-intercept, right? That's like taking a table and plugging in 0 for x. Notice if I do that, 0 cubed minus 2 times 0 squared minus 9 times 0 plus 18, right? Your output is just 18. So it's your constant term that yields your y-intercept. So maybe that's up here. So I know that if I'm following this function, I'm going to go from here. I'm going to have to hit this, right? Go down through here, and then eventually go back up, right? So the nice thing that starts is you know that this is here, right? And you know that this is here, right? You have to have that shape. So it's really the only way to finish out the picture and make it work. If you're ever not sure about how a picture is, remember we do have the benefit of using Desmos.com. So if you type this into Desmos, you should get a picture similar to this. Remember, ours is just a sketch, right? We're not being super precise with how low this is. So keep that in mind. Now let's go back to the end behavior. The end behavior, we're thinking about like long term. And the way that mathematicians generally write this out is they say something like, as x goes towards infinity, as x gets bigger and bigger and bigger. And when I'm talking about that, I'm talking about like as I go all the way this way, on and on forever. Remember that end behavior goes up to the right? So because of that, our y is going up, right? That's because of that green end behavior that we've got highlighted, going up. The second idea is that as x goes towards negative infinity, as it goes towards the left, remember going towards the left, right? Our function is going downwards. So the y value, or the height's continuing to go down and down forever and ever. So y is going to go towards negative infinity. So this is just an idea of thinking about what happens when we go on and on forever. And I'll pull this up in Desmos so you guys can see what that looks like. Okay, so here I've got my graph in Desmos. I can see the negative 3, positive 3, and positive 2x intercepts. It also looks like this point goes down about a little less than 2. You don't need to be that precise though. Really, you just need the intercepts. And remember, if we zoom out, we were able to figure out that y-intercept was over here at 18. What's kind of interesting, I think you guys should be able to see both screens. It's my hope when I'm opening them both up at the same time. What's really interesting is if we compare, our sketch was just assuming, okay, it hits at 18. What's kind of interesting is if you actually look at the real sketch, it looks like it kind of peaks and goes down through 18. Now don't worry about that. When we are doing our sketches, we do not have to have that level of precision. It's really interesting to see though. So what I'm looking for in a sketch is the intercepts, so your x-intercepts and your one y-intercept, and I'm looking for the arrows to indicate where it goes. Notice my function, if I zoom out, right, it continues to go up and down. So as x gets bigger, right, bigger and bigger numbers, your y value just keeps going up, and as x gets smaller, it's going to keep going down. So going back to our examples here in our notebook, I'm going to have you guys try this next example on your own. So I want you to try this one. To get the leading term, you will need to multiply that out. So you're going to need to distribute this in order to get the leading term. Okay, and I would just do that scratch work on the side. Once you've multiplied it out, it will look really similar, right, to how the first one started. And you should be able to start filling things in to the table and then draw your best idea of a sketch. Unpause when you're ready to double check and compare against mine. So before I do the full solution, so here is the multiplication. It's a lot of multiplication, so follow along, pause the video if you need to. I multiplied out the yellow bit and the green bit. Notice there's a negative sign in front, so I did distribute the purple. If you look at the highlight, the purple that negative got distributed to x squared, negative 2x, and plus 1. And then I did all the huge multiplication table and got my final function, which is written at the top as well. So my leading term, right, here's my leading term, negative 1x to the fourth if you want to put the number. Leading coefficient is just that negative 1, right? Notice it's kind of highlighted here for you. The degree is the power of the leading term, right? The highest power you see, and that's going to be a 4, which means it's also going to be quartic. The constant term is just tacked on the end, which is that negative 4. Kind of color coding it to keep purple. That also means that the y-intercept, if I plug in 0, anything with an x goes away. So remember, your y-intercept is just the constant, which is kind of nice. Your end behavior, I'm going to do it over here because I'm running out of space. So I see it's even, so it's either kind of a parabolic shape, right, facing up, or both facing down. The negative sign in front means it's going to be down, something in the middle, and down. Okay, and then my zeros, it actually started in factored form. So what minus 1 makes 0? That's a positive 1 if you look at the top. Right, I'm looking right here. That was already in factored form. And then what plus 2 makes 0? Be negative 2. So I'm just going to get those put in. Add in my x-intercepts. And my y-intercept is a negative 4. 1, 2, 3, 4. Now remember, it's facing down and down, so down and down. Now here's one caveat. I'm just going to make this a little bit more curvy. One caveat is some of you guys might think, okay, I need to connect the dots in a way that makes sense, so I'm going to kind of go like through here. I got to hit my y-intercept, and I kind of come back here, so maybe like that, or you know, maybe your last line kind of goes, if I kind of undo that, maybe you know, your last line might go like up and down, something like that. So that kind of works, but here's the issue. We have added not just 1, but 2 x-intercepts that did not exist before. So we're not allowed to do that. So what that means is I can't go through this. If I go through this, I'm going to eventually have to come down, and that will make another x-intercept. So what I have to do is kind of bounce off of it, hit my y-intercept, and then bounce off this one. And that's really weird, right? One clue for why we have to bounce, a lot of students start noticing some patterns with that, with being squared. I'm going to pull this up in Desmos just to look at it with you guys. Okay, so here it is in Desmos. You can see it looks really similar to the sketch. One connection I do want to make is if I thought about something like, I'll take this away. If I do something like y equals just x minus 1 squared, remember that was a quadratic that had the 1 x-intercept, so because of that shape it bounced off of it. So try and keep that connection, because we did see that happen with our quadratics, that was the case when you had 1 x-intercept rather than 2 or no x-intercepts. I'm also going to put in my end behavior, which is as x gets bigger, y goes down, right, long term, and as x goes smaller, y also goes smaller. Okay, and there's some color coding there. So please come prepared to ask lots of questions tomorrow. Tomorrow we're going to have a couple of graphing practices to make sure we're feeling good on this. So I'll see you guys then.